Okay, we're going to start our discussion of L'Hopital's rule, about talking about why something like that might be true, and then do a couple of elements that we haven't actually been able to do so far before. The reason for L'Hopital's rule being true is if we start looking near x equals a, which is what we always do when we're doing limits, it is always true that if I'm looking at the function on top and the function on bottom, I should be able to just look at the linearization on top and the linearization on the bottom. So I'm going to get f of a on top plus f prime of a times x minus a, like that. Let's move this over a little bit so we can see something. And on the bottom, I should just get g of a d prime of a times x minus a. So it should always be true that the limit of the left-hand side is equal to the right-hand side. But L'Hopital's rule says we're not looking for specific limits of fractions. We're looking for specific limits of fractions where the top goes to 0 and the bottom goes to 0. Well, if the top goes to 0, right, plugging in a right here makes this 0. The only way the top can go to 0 if this part here is equal to 0, so it's really gone. And if we're doing, the bottom also goes to 0. When I plug in a for x here, this part just gets to be 0. And so the only way the bottom can go to 0 if this part here is also equal to 0. So in the specific case of L'Hopital's rule, what we're really looking at when we're looking at the linearization on the top and the linearization on bottom is something that looks like that, right? With the f of a is gone and the g of a gone, well then the x minus a's just cancel, right? And all you're left is with f prime of a on top and g prime of a on bottom, and that's essentially what L'Hopital's rule says. It says if you want to know how big the fraction is getting, and these two parts go to 0, then what you're really looking at is f prime of a on top and g prime of a on bottom. So that's why L'Hopital's rule works. There's lots of special cases and stuff, but everything is actually just an outgrowth of what we just mentioned. Let's do two limits that we would not have been able to do before. So here's limit number 1. This is quite a famous one. I would say in a lot of calculus classes, they spend a lot of time on this one. But the way we did this, when we found the derivative of a sine, we drew a circle and used it. We didn't actually try to do a bunch of fancy limits with identities. So we actually avoided all that, and now we're in good stead. Now, if I just try to plug in, right, I'm going to get a 0 on top and a 0 on bottom. Now, by the way, that's an essential part of using L'Hopital's rule. Out of 14 points, that's a point, that's a point. Now, you always have to tell someone when you use L'Hopital's rule, and I just think, well, actually, on the AP exam, just putting a little L hop there over the equal sign is fine. Now, what are we supposed to do? We're not supposed to take the derivative of the fraction. That's not what it said. It said take the derivative of the top and take the derivative of the bottom, then try taking the limit again. Well, now I can just plug in, and I get 1. And so we get 1, and that's the answer. And that's actually a very, very important limit in all of calculus. We managed to avoid it when we took the derivative, and we can do it with L'Hopital's rule really, really easily. That's the first fundamental application of L'Hopital's rule. Another one that's just as important, and they actually refer to it a lot in pre-calculus, is I'm going to take the limit as x goes to infinity of something like x on top and e to the x on bottom. Now in a pre-calculus class, what you're going to do is you're going to say the bottom's exponential and the top is linear, and exponential functions grow faster than linear. But you know what? They never proved it. It'd take 3 or 4 days to actually show that, and it's not worth the time. On the other hand, if we're using L'Hopital's rule, it's not so bad. Now, how does L'Hopital's rule work? You have to make sure you're in the case. Now, see, the top is going to infinity, and the bottom's going to infinity, and so it actually matches one of the two cases of L'Hopital's rule, where it's 0 over 0, or some kind of infinity over some kind of infinity. Now, you always want to make sure you tell everybody we're using L'Hopital's rule. Now, how does L'Hopital's rule work? You don't use the quotient rule. You take the derivative of the top, you take the derivative of the bottom, and then you try to take the limit all over again. And one thing you should remember is that we still have to do our limit stuff. For example, we can't plug in infinity, and you shouldn't try, and you should never write 1 over infinity. Just never. What we're going to do is we're going to say, how big is the top getting? Well, the top is always exactly 1. The bottom is getting huge. And the limit's asking us how big the fraction is getting. Well, the fraction is getting closer and closer to 0. That's the same thing as saying the limit equals 0. And this is the first case where you actually get a chance to prove that an exponential function dominates a linear function. That's the end of this section.